This video is mainly going to start handout 7, talk more about test functions to keep developing the fundamental theory of distributions. But first, unfinished business from handout 6, just really quick about delta double prime. We'd like to look at a smooth approximation of delta double prime, just like we had a smooth approximation of the Gaussian, the delta as a Gaussian getting narrower and taller. We also saw a similar thing for the derivative of delta, so these guys go to delta, these guys go to delta double prime when we took the derivative, and it was important that that became an epsilon squared on the bottom. It had to be quite tall. And then similarly, if you take two derivatives of this guy, you're going to get a 1 over epsilon cubed. Oops, that's a delta single prime, as an approximation for delta double prime. So let me just show you real quick what that looks like on a computer plot, so it'll be nicer. So here's the Gaussian, and again, it doesn't have to be a Gaussian, anything really, a decently smooth function that has that peak in the middle will work really nicely. Then the solid but not thick line is the derivative, so that's that up-down pulse that we've talked about. And so now the delta double prime, which is still somewhat mysterious thing that showed up in the I equation, the current equation, in that last case, is going to be an up and then double down and then up hump. And it's interesting and it's very significant that that's double the height going down as the up humps. And if you look at how that's going to behave when you squeeze it, then here's that same function but just shown on a different scale. Up, double down, up as the dark line, and then when you squeeze it, it gets, I'm not squeezing it by much, I'm just taking it in by a little bit of a factor coming in, but notice it's getting a lot taller, and then the dotted line is getting much taller even though I'm not squeezing it very much. So that's what you could picture. If you want a picture of delta double prime, it should look like this in your head, of the up, double down, up, and then squeeze it until it's very tall and very skinny. Okay, so let's go to handout 7. This is part of our unfinished business, part of our to-do list. We need to understand more about test functions. We at least know what they are. We still haven't really fully defined a distribution, but we will pretty soon be able to have the exact precise definition. But in particular, we do know that a distribution like T is a map from the space of test functions, I'm going to have a notation for that in a second, to R. It's a linear map, and we're going to have to say more about its properties, but we really need to understand this domain, the inputs. And remember, these are the sort of the thermometers that we use to measure this physical object T. Okay, so let's just I'm going to call this script D, or eventually we're going to do this in Rn, so this is the test functions on just R to start with, okay? And we know what it is. We're pretty sure, or we can be somewhat confident, and I'll just say this is it. We're not going to change it anymore. It's functions from R to R that are smooth, and so that's just going to mean infinitely differentiable. It's just a lot more to write out or say. Infinitely differentiable. Smooth sounds like a little bit more of a slipperier word, but we really are always going to mean infinitely differentiable by that. Or C infinity is another way to say that. And we also know it has to have compact support, because otherwise all these integrals that we were using to think about how to think of like a function as a distribution, none of those are going to be guaranteed to converge. Okay, so that's what D is. It's smooth functions with compact support. But there's a huge issue there, which is that it's not at all trivial to verify that there's anything but the zero function in that set. Okay, so, and if you use a certain intuition that most people have coming out of calculus class, even a pretty good calc class with some theory, you might be convinced that there is no such thing and this theory is completely impossible and vacuous. Okay, so that's what problem 1 is about. There's more to say about this than what I have in the main handout, and that's why I'm going to create a supplement to this as well. We don't really need that there, but for now let's just do a little bit. So we're going to look at a contrast to what are called analytic functions. And I'm not going to define that quite precisely until the end of this problem. But here's what we're going to do. The usual way, or a very common way to think about and analyze and get precise results about and approximations for a smooth function is its power series. And one gets the impression in calc that every smooth function has a power series. Well, let's see what happens if we assume a function has a power series and also has compact support, and we're going to get into trouble. Okay, so we're going to assume, we're going to start out with the most basic assumption and weaken it a little bit. Assume that this is true, so notice the power series is centered at 0, mainly for convenience, okay, and that this holds for all x. In other words, infinite radius of convergence. This is an accurate thing on all of R. Okay, and this implies that f is smooth. Standard result about power series that I won't go over is that you can differentiate power series term by term if you're within the interval of convergence. If that's all of R, then you can keep differentiating forever. It's going to be a smooth function, infinitely differentiable. Okay, so now we're going to assume that f of x, f vanishes on some interval of, not just the empty set, around the origin. So it's vanishing here, and we'd like to have something that can vanish sometimes and not vanish other places. That it could vanish and then eventually do something more interesting, And the problem is that that's going to be impossible if it's given by a power series. And that's pretty easy to show, okay? Because we know what these coefficients are. The easy part of Taylor's theorem, the part that doesn't talk about remainders or convergence or anything, it doesn't even really deserve to be called the theorem almost. It's such a basic calculation. It says that you can get these a sub k by differentiating at 0 and then make sure you put in the over k factorial. Okay, if this function is 0 everywhere near the origin, all those derivatives are going to be 0. They're all calculated as limits as you approach 0, and eventually those limits are going to be between minus epsilon and epsilon, and these are all 0. So that means this function is the 0 function. It's the 0 power series that represents the 0 function. Okay, so that's obviously an issue, and let's push that a bit further. You might think it was important that that interval was right around 0, and that the expansion, the power series expansion, was around 0. Okay, so again, we have that it does expand in a power series around 0. And now let's assume there's some other little interval out here, x0 minus epsilon to x0 plus epsilon, on which the function is 0. Right off the bat, it might be, maybe I can't use that same argument, maybe doing interesting things here, and so it's all interesting and everything's good. Okay, but it doesn't take too much more work to show that this has to vanish as well. Okay, so first of all, if we knew this was a power series expanded around x0, then we could use exactly the same argument. Okay, but all we have to do is let's just define g of x to be f of x plus x0. Okay, that takes this function and translates it back to 0. Okay, so now this is around 0. Okay, la 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 la. Okay, now we're going to go ahead and calculate the Maclaurin series of that guy. The coefficients are not a sub k. They're related in an interesting way with the x0 and binomial coefficients and stuff like that. We don't actually turn out to need the exact relationship. Okay, the thing is the bk's are still derivatives of this function at 0 over k factorial. Those are still going to be 0. Okay, and so g is the 0 function. But wait a minute, they were just translates of each other. Okay, and so f of x is 0 for all x as well. Okay, so the main thing is when you've got a power series that works for all x, then it really is there's going to be a power series for that for all translates of x, or equivalently you can we can change the base point. The exact coefficients are going to change in a slightly complicated way, well, somewhat complicated way. But the thing that's easy to show is if some of them are 0 when you translate, then the other ones are 0 as well. That's just it's just going to be dead. So this is really telling us something. This is saying that if we thought the way we were going to create these functions was through power series, and if they were going to look like sine and cosine and e to the x and stuff like that have nice power series, then that's really a bad intuition. In particular, now that this is really the punchline for this part of it, if f is, if it's representable by a power series with infinite radius of convergence, and f has compact support, that means compact support, then, okay, well, what does compact support mean? It means that it's 0 out here, it can do whatever it wants, but eventually, again, it has to be 0. Like, outside of like minus m to m, it vanishes. Okay, so just pick your x naught out here, and your epsilon in part b, so that it's out here. And so then f equals 0. Often when we want to say something's identically 0, we put a little third line. F is identically 0. It's not just 0 some places, it's the 0 function. Okay, this seems to be really disturbing because this is a very standard way to create smooth functions. Often people's intuition is that all smooth functions are of this form, because so many of our popular ones are, like trig functions and polynomials and exponentials. And it seems like, but the thing is, we were trying to create test functions that are like these idealized thermometers. It's 0 outside of here and here, it's non-zero here, and we can probe with that thing. Okay, so the key thing is that intuition is just wrong. That smooth functions have to be given by power series. Okay, so let me talk about something that's I'll go into depth more in the supplement. The real definition is a little more, a little less strict than what I was doing here. F is called real analytic on all of R, and it's still going to be on all of R, if for all base points A in R, F is given by a power series expansion based at A, and I hardly need to say this, but let me emphasize it, with some positive radius of convergence. So in some neighborhood, it's given by a power series. So on all the real line, no matter where you are, here's A, there's some way to express it as a power series here. And we're not quite sure exactly how that relates to like some other A prime, how the power series relates over here and what the radius of convergence is and everything. But it says that locally at near every point in R, it's nice. Okay. Now for our test functions, we want them to be nice everywhere. We don't want them to just like blow up somewhere. So that's not an out. So it's not really, the point is not that this is too strict. The point is that this idea that locally it's given by a power series is really not what we want here. That's not, and it's too restrictive, much more restrictive than being a smooth function. Okay, so in the next video, we'll introduce a very cool function, which is something that shows that you can have a smooth function that's not given by a power series and that has the behavior that we want. But the point of this first problem was to show that we need to go beyond that power series understanding to get the things that we want. But the next problem will show that that is really possible.